So in this next about an hour and a half, so we'll go some through this today and then we'll finish this up tomorrow. I want to talk about X-ray imaging, computed radiography, digital radiography, and fluoroscopy. So let's just talk about some imaging basics, and maybe this will be good to get through tonight if I can, to just get through contrast, resolution, and noise, and then we'll pick up with the next part of this on our next talk. So contrast is what really allows us to perceive something in the image. I mean, it allows us to see on the film or the PACS two areas as being different in the image. In medical imaging, we're really concerned with three types: object contrast, subject, and image or detector contrast, if you will. So what is contrast? Well, mathematically, if you think about one region of the image versus a background of the image, it's really talking about, what's the difference in intensity values in those regions. And there are a number of different formulas for doing it. If you looked at kind of what's the Hounsfield units in one area versus a background on a CT, or the brightness on an X-ray, that you could use a measure like this. On MR, what's the signal intensity in one area versus the background area divided by the intensity in that area you're interested in? Or in nuclear medicine imaging, how much activity are you measuring in one area versus a background area divided by that area there? So it's kind of a normalized to that location there. But, conceptually, this is what I want you to understand, right? This is a high contrast image where there's a big difference between the area of interest and the background. And this is a low contrast image, whether this is a radiograph, whether this is an MR, whether this is a nuclear medicine study. What is object contrast? Well, object contrast really has to do with a property of the thing that we're imaging. Is there enough difference in linear attenuation in the object itself in two regions? If there isn't, we have no hope to make an image of it that looks different, right? If there's no difference in linear attenuation in two regions in the image, we're not going to be able to have that show up on an X-ray or in CT. Maybe we would on MR, because maybe there is a difference in the density of protons in that area, right, kind of thing. So in MR, maybe it's proton density. In PET, it's the amount of uptake of a particular radio tracer in those tissues. If two regions have the same object contrast, we can't hope to make an image of them. So we've got to have object contrast. And I want to give an example here. Here's bone, muscle, water, and air. And I've just put their physical density here. So I'm being a real troublemaker, right? I spent 15, 20 minutes trying to explain to you what linear attenuation was, and that it isn't exactly the same as physical density, and now I'm showing you physical density and showing this. But they're closely related to each other. But if I was being more precise, I should really have put linear attenuation numbers here. Notice there's quite a big difference between bone and muscle, but muscle and water are very similar, but they're quite different from air. So there's really good object contrast here. So what about subject contrast? Well, now we're going to irradiate that object, or now after we stimulate that object with our MR coils, we're going to listen to the signal from it. And how much signal is produced by those tissues? Or how much do those tissues attenuate the X-ray beam? And the subject contrast is really a measure of that, right? So here's those same tissues, and we've now irradiated it with a polychromatic X-ray beam, KVP equal to 30. And here's the percentage of the X-rays that would make it through 1 centimeter of bone, muscle, water, and air. And notice the difference here, 0.66 and 0.68. These are still very close to each other, right? Still very close to each other. But what if I do that at 100 kVp? Well, remember, these tissues, 100 kVp X-rays, this X-ray beam is going to be higher energy when we apply 100 kVp across the tube than down at 60. And so these are going to penetrate those tissues better. So now the difference here, 0.83 and 0.84, only 1 part difference between those. So the contrast has been reduced by increasing that KVP, right? As a matter of fact, if we went even higher, the amount through muscle and water would be basically identical. We would have no hope to differentiate them. This is the subject contrast, okay? And then the next thing is the image contrast, because now I have to stop those things and detect them. Or in the MR example, I have to detect that signal intensity that's coming out of the tissue and measure it. And that may result in some degradation in that information as well. And that's the imaging contrast. Is there enough difference left that I can make an image out of that? Now, in the screen film imaging days, by the way, anyone in the room still use film for anything? In 2015, I think 5% of the country was still doing screen film mammography. My guess is no one's going to raise their hand and say that they're using any screen film for anything right now. Yes? Someone? Okay, so still some people are, right? In digital imaging, I can leave the development of the image out of the chair, right? With a piece of film, you can underdevelop it or overdevelop it. You could overexpose it or underexpose it, and that contributes a tremendous amount to the imaging chain, right? In digital imaging, we're much luckier. So remember that equation that I showed you? In digital imaging, when the tech is preparing your image for you, they actually subtract this arbitrary constant from the pixel value here in the background and then again here. And if you'll notice, these K's will cancel each other. And so notice now you end up with this equation for contrast that has this constant K in it. And if you wanted to, you could make this K very close to PA. As a matter of fact, make it much closer to PA than PA is to PB. And this number becomes very large. Digital imaging, by adjusting that K factor, you can really work over an extremely wide range of contrast with digital images that was basically impossible to do with screen film imaging. So we don't really use the idea of contrast as much when we talk about digital imaging, because digital imaging is not contrast limited. Instead, we use this contrast to noise ratio, because if you make that K very close to PA so that you get your contrast to be what you want to be, it accentuates the noise in the image. That's the problem that occurs when you do that. And so digital imaging tends to be noise images. So this contrast to noise ratio is the difference between the property at pixel A and the background divided by the noise in the image. And so I just wanted to say that it's a little bit different in digital. But conceptually, we all have a really good idea of what a low contrast versus a high contrast image. And one of the nice things is, at the PACS, we can adjust the contrast as well. We can't adjust it to the same degree that the tech could by changing that constant K. Remember, that's something that the tech did before they sent the image to you. If you ever have an image and you can't see a particular area well, ask your tech to go back and reprocess it, and they'll adjust the K, let them know the part of the image that you want to try to see the best, and they'll choose a K that gives you better contrast in that region, okay? The only downside is the image might get quite noisy in that region. So next thing, we just finished talking about contrast, and next I wanted to talk about spatial resolution. When we talk about resolution, we're really talking about how much can we differentiate between two subtle things. So we actually can talk about contrast resolution, which is what we talked about last time, and now specifically when I say resolution, I'm talking about spatial resolution. And that's the notion of, you know, how small can objects get and I can still see them, but another way to think about it is how close together can small objects get and I can still distinguish them as being separate from each other. And that's this idea of these line pair phantoms that you see a lot in radiology try to capture. If I take one of these and I image them with an imaging system, how well can I separate these as individual lines? And if you had an ideal system and you imaged one of these, an X-ray system, well then if you measured the brightness across the surface of the film, it should be at a perfectly high level at one spot and down at the lowest level. And this should really be a rectangular function if we took a profile across the image. But in truth, we get some blurring at the edges with any system. So maybe a good system would round those edges off a little bit, and a poor system would really kind of blur those bars into each other quite a bit. And it turns out that most systems, as you try to drive to higher and higher resolution, in other words, if you take a look at more line pairs per millimeter, you go from a very good fidelity resolution properties to much poorer properties. And every system has some limiting resolution where basically this looks like a flat line. When you take an image of that phantom with very high number of line pairs per millimeter, it just looks like it's uniformly gray, if you will. And that notion, if you'll take the height of these curves for each of these line pairs, so here's 6 pairs, here's 8 pairs, I think this is 16 pairs or so. If we'll go ahead and plot those, here's the red, here's the blue, the 16, we're plotting the height of the curve from here to here, and the purple one from here to here, the height of the curve versus the number of line pairs, we see that that drops off, that height drops off. And this is referred to as the modulation transfer function. And the nice thing about this is, if I know what the modulation transfer function is for my X-ray tube, because it has a certain focal spot size and therefore has a limiting resolution, and I know what the resolution properties of my detector are, because it doesn't have perfect resolution properties, I can multiply the two MTFs together and it'll give me the resolution properties of my overall system. In looking at this, just keep in mind what a really good system should do, right? A really good system should be flat, way out here, even up to very high frequencies, right? No matter how many line pairs per millimeter you get, you still get very close to 100% of that true height. So with the MTF, the flatter that looks across, the better the resolution properties. The next thing I wanted to talk about was noise. Okay, so noise is that random fluctuation in the image intensity about its true value. And quantum model is due solely to statistical variation. Sometimes the X-ray makes it through, sometimes it doesn't make it through, and whether it does or not is determined probabilistically. And quantum model is the most important source of noise in our imaging. It turns out that the probability, the statistics that govern whether an X-ray makes it through an object or not is governed by something called the Poisson distribution. And that's very nicely approximated by the Gaussian or the normal curve, the bell curve, once we get up above a mean of about 10. And certainly most of our X-ray images have more than 10 X-rays per pixel, so that approximation suffices. It has a mean of n and a standard deviation of square root of n. So what's interesting for these statistics is that really if you tell me the average number of X-rays that entered a particular picture, that would tell me both the mean as well as the standard deviation, because the standard deviation is just given by the square root of n. So noise is perceived by us. When we look at the image, noise is perceived by us as something called the coefficient of variation, or if you will, the relative noise. You know, if there were a lot of X-rays, we perceive the noise differently when there are very few. And so let's take a look at this. Right here, if we had 10 photons per pixel, if we take the square root of that, which was the noise as we talked about, that's 3.2. Now if we go up to 10,000, the square root of that is 100. So 100 is quite a bit bigger than the 3.2, but our eye perceives what we call the relative noise, which is this noise number divided by the number of photons, n. So this 100, right, divided by the number of, the square root of that noise divided by those number of pixels. So here that is expressed as a percentage. So 100 divided by 10,000 times 100 to get it in a percentage. The relative noise here is 1% compared to the relative noise down here, which is 32%. So that's the number that we perceive when we visually look at the image. Just as an example, here's a phantom of a pelvis radiograph obtained with 2 milliamp seconds, so current, right, times the time, and here at 160, right, so 80 times more MAS. And you can see the speckling here compared to here. Here's a contrast versus resolution versus noise, right? We're now putting all of those three things together. Notice we've got some different size discs, right? And they're in a background setting of some noise. And there's a row of them which are higher contrast than a column of them, which are higher contrast than the next column and the next column. And you can really get a feeling for how both contrast and spatial resolution in conjunction with noise play a role in how conspicuous a lesion is to us. There's an interplay between all of those quantities. Certainly we can make that much better just by driving down the noise, but of course that means more photons, right? That means greater dose to the patient. So I want to talk a little bit about general radiography. I'm going to just mention film very briefly before I move on to digital imaging. As I asked yesterday, right, there are very few in the room who are still doing much in the way of film imaging, but it's helpful sometimes to make analogies to that a little bit. You know, film, we had this silver halide emulsion on this plastic backing, this mylar backing. And when visible light, film does a really nice job stopping visible light. But that thin silver halide layer really doesn't do a very good job stopping X-ray energies. So instead we had to put something in front of that did a better job stopping the X-rays and converting them to visible light that was better matched to the absorption characteristics of the film. In the film days, we talked about the fact that we exposed the film and then we developed the film. And so we really had these issues with these underexposed ranges and these overexposed ranges where you really weren't able to distinguish structures anymore because of the poor contrast. And film only worked well in that range. And I put this slide up because it really shows the linear response of digital imaging, which really has a nice response over a very wide range of exposures. So as I mentioned, you know, we really need to put something in front of that film since it just does such a poor job stopping those X-rays. And films are used screens are used to do that. And there's a very similar thing that we're going to see putting in front of some of our indirect digital detectors. And that's why I still want to talk briefly about screens before we do that. So screens really improve the efficiency. They improve the use of the X-ray energy that makes it through the patient and converting it to our image. So they do a better job stopping those X-ray photons, right? Usually made out of a material that has a higher Z than the material that makes up our detector, either the film or our detector elements on a digital detector. Phosphors and scintillators, as I talked about, analogous to screens that we use in our indirect digital imaging. So here comes our X-ray photon in. It strikes this screen material, and it converts this X-ray energy into multiple lower energy light photons. Right? So we see that here. So the good thing is now these are much more easily stopped and detected by a CCD camera or by film in the old days. The bad thing is that they disperse out a little bit and therefore cause some blurring in the image. When we talk about screens, we can talk about this absorption and conversion efficiency, right? Doing a better job kind of converting some of that X-ray energy into lower energy photons that can be used to make the image. And I want to talk briefly about a concept called absorption efficiency and conversion efficiency. So with absorption efficiency, if you just make the screen a little thicker, it'll now stop more of the X-ray photons and convert them to that lower energy light. The downside is there's now a thicker screen for that light to disperse in, so the light has more distance to spread out after it's generated, and so your resolution properties go down a little bit with a thicker screen. So better efficiency, but you sacrifice a little bit of resolution. The other thing you can do is just make them out of a different material, maybe a higher Z material that does a better job stopping your X-rays. And in that case, you now produce maybe more light with that single X-ray photon than you did with your older screen material. So this is the conversion efficiency. The issue here is now you're going to be able to make your X-ray image with fewer X-rays, right? Because each X-ray is going to generate more light from that. And so this increased conversion efficiency does result in a bit of increased noise in your imaging, because it's really the incident X-ray photons that determine how much noise was in the image, not how much light is produced. So that's the sacrifice that we play by using different materials to stop those X-rays. I next want to talk a little bit about scatter. You know, we've talked about this really being due predominantly to those Compton interactions. Yes, there's a little bit of classic or Rayleigh or coherent scatter, as we call it. This reduces our image contrast. And a lot of imaging that we do, chest radiograph, pelvic radiograph, scatter to primary ratio, the number of detected X-rays that were scattered versus ones that were unscattered, scatter to primary ratio, can be 3 to 1, 3 times as many scattered as opposed to unscattered, or even 6 to 1 in kind of lateral abdominal or lateral lumbar spine imaging. So we always want to make sure we collimate, right? It reduces scatter because it reduces the volume of irradiated tissue. And if you irradiate less tissue, then those X-rays can't end up scattering back into your area of interest. It improves our image contrast, and it also ends up reducing the patient dose. So we always want to make sure we collimate, okay? Scatter is reduced at lower kVp. That's because there's an increase in the photoelectric interactions the lower the kVp is. But that's not always practical, right? When we're doing a lateral pelvis in an adult, it's not practical because we've at least got to get enough X-rays through them to make an image. And so in that case, if you go to a lower kV, the MA that you have to get is so high that the dose can maybe be prohibitive. So here's that patient. Here's our scatter versus primary. There are all those scattereds coming out. And I emphasize again that there's a lot of these here. Many fewer make it through the patient. Here I've shown a scatter to primary ratio hitting the screen that's closer to 1 to 3. And I told you that the true number is actually closer to 3 to 1, right? More scatters than primaries. There those are. That's what we're talking about. We're ignoring everything that was absorbed completely. We're ignoring everything that was backscattered and didn't end up hitting the detector or the film. So as I mentioned before, right, we're going to collimate. We're going to reduce that kV when it's at all possible. We may use an air gap, and the other thing I want to talk about is maybe using a grid. I want to make this point quickly, though. Here's an example of where they use some different diameter phantoms, and they use different field of view sizes, where on that phantom they opened up the field of view to different sizes, and they looked at what the scatter to primary ratio was. So look at here. Here's a very small phantom, 5 centimeters. And even if the field of view got bigger, there really wasn't a whole lot of scatter. So again, right, pediatric patients, small parts, right? Scatter is not a huge issue there, and that's going to be important when we talk about grids in a second. Larger patients, getting our field of view size down as small as we can possibly get it to see the area of interest becomes very important to help keep that scatter to primary ratio down. Air gaps also reduce scatter. Does everyone see that if you move the object, the detector away from the object, you give room for some of these scatter events to escape and not strike the detector? So using an air gap can help. And that's why we don't use grids in magnification mammography, right? Because there's an air gap there that helps keep our scatter down. Grids are another way. Grids are very similar, if you will, to the collimator that's used in nuclear medicine, and I want you to keep that analogy in mind here. In nuclear medicine, we're actually going to use that collimator to focus, if you will, the gamma ray energy onto the camera. Here we're going to use it to reject scatter. So the holes are lined up specifically at a particular distance, at a particular angle to the X-ray tube. So primaries that aren't changed in terms of their direction should pass through the holes. Yes, occasionally one of the primaries may strike one of the pieces of lead or whatever material it's made out of and not make it through too. So grids reduce the primaries as well as reducing the scatter. It's just that they reduce the scatter much more than they reduce the primaries, okay? So our overall ratio of scatter to primaries gets much better when we use a grid. And there's that grid ratio, the height of the holes divided by the width of the holes. As I mentioned, they decrease both primary and scatter, greater effect on those scatters. Longer and narrower the holes are, the more rejection they give. Grids always require an increase in the number of X-rays, right? Because the number of X-rays that are going to hit the detector go down with the grid. So you've got to provide an increased dose to that patient. And the amount of increase in MAS that's required is referred to as the Bucky factor, right? And that's an increased dose to the patient there. We usually place the grids are in a little bit of a reciprocating frame. They vibrate just a little bit. Not even, kind of almost the diameter of the hole width is how much they vibrate back and forth, so that you don't see the pattern, right, on the radiograph when you look at it. So here's if the length of the holes divided by the width of the holes were 5, 8, and 12. Notice that holes here convert a 4-to-1 scatter to primary ratio to a 1-to-4 scatter to primary ratio. But the price paid is a need for a 5 times increase in the dose to the patient, all right? Here is a chest phantom done with the grid in place. Here's the same phantom done without the grid, and everybody sees the reduction in the contrast that's made because of all the additional scatter. For portable studies, stationary grids are used, and they have lower grid ratios and moderate line density. And sometimes you see them, especially if they're not placed very well on the portable studies. I'm sure some of you have seen those artifacts. I'll show you an example there. We already mentioned that small parts neonatal patients don't require grids because there's minimal scatter to start with. We certainly don't want to put a grid in there, right? It'll be increased dose that we'll need, and when we didn't need the grid in the first place. And then here's one of those misaligned grids that you'll see sometimes. This one's really prominent. Sometimes they don't stand out quite that prominently. Talk a little bit about digital imaging now. We certainly use both grids and something similar to a screen in digital imaging. You know, really, the advantages of digital imaging, right? We can be viewing images at multiple sites. We've mentioned the fact that they have a wider dynamic range. They're not contrast limited. It decouples the recording, the displaying, and archiving tasks, right? It used to be you had one piece of film. The image was recorded on that piece of film. You had to read that piece of film. That piece of film was stored in a jacket for archival purposes. Right now, multiple people can all be looking at the image simultaneously, kind of thing. People thought it would lead to higher patient throughput and decreased dose. Sometimes some of the things you think might happen don't quite happen there quite as well. Unfortunately, it really required a lot of new, expensive equipment, and so it took a while, and there was kind of a natural transition from film to CR, and now to some of these more direct digital systems, because CR most really closely matched what was previously being done with film, and so it was kind of a natural progression there. We need some high-speed networks, of course. Some of these images require a tremendous amount of bandwidth. And they do have decreased spatial resolution compared to film. And some people thought that may be prohibitive in terms of their use, but that really hasn't been the case as we've gotten better and better resolution digital imaging systems. Still not quite the same as screen film, but getting closer to doing that. There's a number of different digital detectors that are out there, some gas detectors, and if anyone has a volume zoom, one of the old Siemens 4-row CT scanners, that actually was one of the last things that had xenon gas detectors in it. But more likely they're either crystal, scintillators, or phosphors that we'll talk about, or they're solid-state semiconductor, amorphous selenium detectors, and I'll mention those in a second. You know, a gas detector is pretty simple. X-ray comes in, interacts with the xenon gas here, liberates some charge, and we just measure the amount of charge is proportional to the X-ray energy that was detected. Crystals and solid-state detectors, you know, there's a number of them that we'll hear and talk about in different imaging: sodium iodide, cesium iodide, bismuth germanium oxide, and in PET, barium fluorobromide. In atoms, we talked about electrons existing in that shell configuration. In crystals, they're shared and they exist in these band configurations. And solid-state crystals have special properties between their inner band, their valence band, and their outer band, their conduction band. And it turns out that photons can transfer energy to those inner band electrons and move them up to those outer bands. That electron may immediately fall back down into its valence band and give off a little bit of electromagnetic energy in the kind of the visible light range. And things that do that immediately, that return immediately and immediately give that light off, are called scintillators, right? And things which take a little bit more time to do that are called phosphors. So scintillators and phosphors are very similar things. It's just the timing at which it takes for those outer band electrons to move back down to those valence bands. In some phosphors, those electrons that move to that outer band are pretty stable sitting in that outer band, and they'll stay there for a fairly significant period of time. And we can help that process out, help move them back down into the inner band by inputting some energy into the system. And those are called photostimulable phosphors, and those are what CR, computed radiography plates, use. So let's look at that a little bit. Scintillators, we're going to see a lot about scintillators in nuclear medicine, right? X-ray photon comes in, as soon as it interacts in the scintillator, it converts that high energy X-ray photon energy into multiple visible light photons. Very similar to the screens, right? Screens are made out of a scintillator material that I talked about. Here's a photostimulable phosphor, right? X-ray energy comes in, it moves some of those things from that inner to that outer band, some of those electrons there, and it stays there fairly stable. And then we can use a laser light to stimulate that region on this phosphor, and lo and behold, we get this production of a lot of lower energy photons, visible light. In other materials, right, I want to move away now from scintillators and phosphors, called photoconductors, that X-ray energy is directly converted to electrons, the flow of current. So that X-ray energy is directly converted through to current. We don't need this intermediate lower energy photons, visible light kind of photons. And those are called photoconductors, and I'll show you an example, some of those. Computed radiography, when you hear the term, really refers to imaging using photostimulable phosphors, okay? And digital radiography, when used appropriately, includes CR as well as digital imaging performed with various other types of detectors, like photoconductors, and I'll show you that example in a while. I think I've said all of this about photostimulable phosphor, so I don't think we need to go over that again. The thing I want to emphasize at the end here is that the amount of light that gets emitted is proportional to the exposure at that particular point on the plate. So that determines that how much light we get there, right, determines how bright that point on the phosphor is going to end up being in the image that we create. The phosphor at the end is then erased with an intense white light, because in truth, as you stimulate the phosphor, some of those electrons have stayed in the outer band, and you now want to move them all back to the inner band before you use the plate again. Otherwise, you end up with a little bit of a double exposure. Okay. You've got to process that plate within a reasonable amount of time. If you go take a radiograph with a CR plate and wait 8 hours, the image quality is going to degrade quite a bit, because some of those electrons are going to move on their own from the conduction back into the valence band. And so after about 8 hours, the image quality is degraded to the extent the image isn't really usable. And just like film, photostimulable phosphors can be double exposed, right? The tech can accidentally take another image on top of the first one, and you can have a double exposure. So here's screen film foot radiographs, right? Low exposure, mid exposure, high exposure. And one of the big benefits of CR is, like we said, that more uniform response, really, that linear response across a wide range of exposures. When CR was first introduced to the workflow, it was very similar to the screen film workflow, right? You expose the CR plate, you pop the plate into the reader. Back then, they even digitized a film of it. Now that would just get sent to PACS after the plate was read. And that film was delivered to the reading room, and the film was archived after reading. So it was a nice natural replacement for film. It didn't require everything just be thrown out the door, if you will. Once adequate packs, archiving systems, and networks were available, now you could expose, read the CR plate, and transmit that digitized image. And I'm sure most of you do a lot of that today. By the way, CR still predominates, although that's changing very rapidly. Direct digital imaging, I think, is going to supplant indirect digital imaging with CR, photostimulable phosphorus, pretty soon, and has already in certain areas. So digital radiography, CR plus some other things. In indirect systems, we convert those X-rays into an electronic signal by first converting them to lower energy light photons, right? In direct digital radiography systems, we're going to convert those X-rays directly into an electrical signal or current. Now, some of you have probably said, you know, I've got a beautiful CCD camera on my cell phone these days. Why don't we use a similar thing and just put that on the backside of the patient and take a picture there? And the reason for that is those amorphous silicon, those transistor type CCDs, those charge coupled device arrays, have no stopping power for high energy X-rays, right? So that kind of system doesn't work. You really need an indirect system in order to make that work. Well, you'll convert that energy from high energy to low energy and then detect. So a beautiful image from the physics modules online, right? Here's film screen. Here are the indirect techniques. Here is CR that we've talked about, where you have the storage phosphor, you stimulate it, then you've got to do the readout, right? And the readout, that charged coupled device, like a camera almost in your cell phone, if you will, takes an image of that light that's being read out when we stimulate the phosphor. There's another indirect that uses a scintillator, right, instead of a phosphor, and some of the flat panel detector systems use this. Remember, these give off light immediately. You don't stimulate them. So they're not useful for going and doing a portable X-ray and coming back down to read that, right? The image has to be read off as it's being exposed, if you will. And that's still done. That high energy X-ray light is converted to this visible light that's read then by a amorphous silicon or thin film transistor array CCD camera. We're going to talk a little bit about direct digital, where now these X-rays directly interact with some amorphous selenium, higher Z than silicon, amorphous selenium detector, thin film transistor array. And I'm not going to talk anything about direct photon counting devices, but that's the next generation of what we're going to see. So here's computed radiography. We already talked about it. I'm not just going to leave the picture there for your reference. Indirect DR with a thin film transistor array. Thin film transistor arrays, it turn out, can be read out much quicker than a CCD array in terms of camera, and I won't go into why that's the case, but that's one of the reasons we like those better, especially on things where a flat panel fluoro system where we need images sometimes in a fairly quick succession to each other. The disadvantages compared to a CCD is less of the surface area of those are photosensitive, so they're going to detect less of the visible light. And I've shown you that they can be used in both indirect and direct. You saw the amorphous silicon and the amorphous selenium ones in that picture. So here's that indirect using a scintillator. We've got that photodiode, and then we've got our array reading that out. And here's direct digital, where the X-rays strike this photoconductor, and then we've got that array just below that. And what's really nice about this is the X-ray comes in, and now instead of producing lower energy electromagnetic light phenomenon, it releases charge in this material. It releases electrons in that material. And if we put a little bias voltage, positive voltage here, negative voltage here, the electrons will move in one direction, and the hole, if you will, the space that the electron left, will move directly down to the thin film transistor array. So unlike our scintillators and our phosphors and our screens, we don't get that spreading out of the light like we did there. This electron moves to the closest, linearly down to the closest point onto that thin film transistor array. So nice resolution properties here. I'm going to show you cesium iodide and why we use it in some of the flat panel detector IIs, digital detectors, because it helps eliminate some of that spreading of the light that we talked about. And I think I put that picture here. Does everyone see that cesium iodide grows in these beautiful needle-like projections? Unfortunately, they're very delicate. But what's nice about that is when light comes in and strikes one of those, the light that's created there, that scintillates from there, travels right down that needle and can't spread too much out laterally from that point. So it helps to have some, improve some of the resolution properties. So scintillators and photoconductors, right? Photoconductors most often used in direct flat panel detectors are selenium-based. So the Z is 34, the K edge about 13. Now we've talked about if we could match the K edge to the average X-ray energy that we're imaging with, that would be a really good thing, right? Because our probability of interaction would be much higher. And this is 13 kV is much too low, right? We'd really like to get that up into the 30, 40, 50, 60 keV range to really match that nicely to the K, the mean energy being produced when we do fluoroscopic imaging, let's say with 80 kVp across the X-ray tube. So newer materials are being developed that use, cadmium, telluride with a little bit of dope with a little bit of zinc, mercury iodide, lead iodide, and that have a higher K edge. And I think we'll see those come into introduction, right? We'll have better efficiency of stopping those X-rays and converting them to electrical current. CR, photostimulable phosphors, are great for portable exams. You take them up, image them, bring them back. They have a really wide dynamic range. Digital systems allow for the image to be viewed immediately at multiple locations. And we used to say CR was nice for those portables, you go up, shoot them, bring it back down, those kind of things. DR systems, well, cesium iodide, that's very delicate crystal, but now if you go to some of these photoconductor materials like amorphous selenium, they're not as delicate, and so you can make a portable plate to go with. And now with wireless technology, you can make a digital plate, right? Take it up to the ICU, and once it's exposed, have that data be transmitted from the plate itself wirelessly to the network in the hospital, so you can have it in your reading room before the tech basically even leaves the patient's room. And that's where we're starting to be, and definitely where we're going to be a few years down the road. Okay, so this is not so true anymore. These systems are kind of coming in line in terms of price there. Well, let's talk a little bit about fluoroscopy. So, and you guys know this, there are a lot of different fluoro systems, whether you're in the IR room or you've got the GI fluoro unit or you've just simply got a C-arm unit. The point is they've got a receptor and they've got an X-ray tube that kind of move in concert with each other. This is in regard to a GI fluoro unit, and I'm actually going to show you one of those and talk about it in specific at the end to just remind you how some of the things that we talked about in these first two talks apply to our X-ray imaging. And I really want to use GI fluoro because that's one of the times when you're in the room controlling the parameters that we talked about necessary to make the image. So components of the fluoro system, that image intensifier or that flat panel detector. So I'm going to ask the same question I asked yesterday. How many people still utilize some fluoro systems with an image intensifier instead of a flat panel detector? So there's a couple people. They are still out there. A few years from now, I think for me to talk about image intensifiers isn't going to make a whole lot of sense because they're being replaced fairly quickly. So with flat panel detectors, right, we don't need a lens or an aperture or a camera system to take a picture of the image being developed on the, the II is like an old cathode ray tube TV kind of thing, and we've got something taking a picture of that. II systems do have that. They have a lens to focus light on the output phosphor of a TV camera. They have an aperture that you can open up to increase some of the light that's let through in that TV camera. I'm really not going to talk about those things. But I do want to talk a little bit about the II because it's something that kind of always confuses folks a little bit. On our old fluoro systems with II, we had this automatic brightness control. So if you had a bigger patient, less X-rays made it through them, and so you got less light output on the II. And so the brightness control would increase the tube current so that the number of x-rays made it through the patient were increased, and the brightness of the image would stay about the same. In other words, it increased the dose to the patient. The automatic dose control unit is somewhat of a similar thing in the digital systems, where it's going to kind of adjust the dose to make sure that that stays fairly constant. Just notice these parameters relative to radiography here. Notice that for KV or it's in a similar range, but our MA values are lower for fluoro versus radiography, and I'll let you guys look at those. So those old image intensifiers, when we did fluoro, we basically worked with a lower dose, and so we really needed to intensify the brightness of the image so we could see that nicely. And so an II consisted of an input phosphor that converted those X-rays coming in to light, a photocathode that converted those lights to electrons. And the nice thing about electrons, we could accelerate them because they have charge, right? We could use positively charged plates to accelerate them and therefore have them strike another part of the II with much greater energy than they initially started with, giving us a brighter image. Those focusing lenses and accelerating anodes basically amplified the signal, and those electrons then hit that output phosphor and converted those flow of electrons back into a visible image, back into electromagnetic radiation. Here's the picture, right? X-rays came in. The material here was responsible for converting X-rays to light. Then this system here took that visible light of lower energy and converted that to electrons. We then sped those electrons up and they struck this output phosphor where basically that process was reversed. And we had a camera system that was taking a picture of what was going on there and displaying it to us. Those image intensifiers, by the way, were made with this cesium iodide once again for some of the reasons that we talked about. When you took a big area on the II and you brought it down to a smaller area on the output of that II, you got some increased brightness solely due to the minification gain, right? If the number of photons hitting this large area is the same as the number of photons hitting this small area, the small area is going to appear brighter. But in addition, we got gain because of that electronic amplification by accelerating those electrons. So you could really end up with a system that amplified that input image brightness, 50 times, which was very, very helpful. Unfortunately, those old IIs had a number of artifacts. They have, even our current ones suffer from lag, right? They're not as quick as kind of movie cameras, so as things move, we see a little bit of persistence and the motion lags behind a little bit. They have something called a veiling glare. If you'll notice that ideally when something struck the input phosphor, if it should look like this, by the time it hit the output phosphor, there was a little bit reduction in that contrast because some of those electrons may have strayed off of path and reduced the difference there. We'd get these pincushion artifacts, because that II was really a glass tube like an old CRT, and so the surface of it had a little bit of curvature to it, so something which was a, parallel grid of holes would look like they had a slight curve to them, especially at the periphery. With the flat panel detectors, we don't have that issue, right? With these amorphous selenium digital detectors, we don't have those issues. They can get read out very quickly. We don't have the pin cushioning, the veiling glare. We still have some lag issues. Bad pixels is the problem now, where you get a dark spot or a bright spot because one of the pixels on the array has gone bad. So let's, in the last few minutes here, finish up talking over one of our GI fluoro systems. So GI fluoro unit, right? You just step on the pedal and you start snapping fluoro spots. And hopefully what we got from these first couple talks as you put them in practice, I want you to think a little bit more about that, right? I want to emphasize, especially in terms of any, examination you might take, right? The first thing you should think about is verifying that you've got the correct patient, right? The correct body part, the correct procedure and everything. And then we'll get started with doing the procedure. And we've got to decide what type of fluoro we need to be using for this procedure, and we certainly want to know if we're using contrast, what type of contrast. But let's talk about what all these buttons, by the way, we have a Siemens fluoro unit, so that's why this is I've got a picture of the control panel on that. I'm not trying to sell any Siemens equipment or anything, it's just what I've got. You can see me in the background taking the picture here. So here I've got circled the KV and the MA controls, right? So remember that increasing MA increases the number of photons in the X-ray beam. It's going to increase the quantity of the X-ray beam. It's going to result in increased dose to the patient, and it's going to result in decreased noise in the image. So if our image is too noisy, one of the first things we do is bump up our MAS. It has no change in the percentage of Compton scatter to photoelectric effect, and so therefore it has no change in the image contrast, just decreases the image noise. And there's no change in spatial resolution. When we increase KV, that increases the average X-ray beam energy. It increases the quality of the X-ray beam. Unfortunately, it also increases the quality of the quantity of the X-ray beam. And we talked about how going to higher KV gives more efficient production of X-rays. So not only do you get a higher average energy of X-ray, you get greater number of X-rays when you do that. The resultant increase in Compton scatter decreases our image contrast, so we typically do this secondary to changing the MA. We prefer to first change the MA to get appropriate image quality if we can, and not change the KV unless absolutely necessary. It doesn't change our spatial resolution. And then I put this because it's very important. If you don't have automatic exposure control on and you increase KV, you increase dose to the patient for the reason I just talked about. You not only increase the quality of the beam, you increase the quantity of the beam. But if automatic exposure control is turned on, which it typically is when we use fluoro, then the dose to the patient actually goes down because it says that the image is adequately exposed with less MA or MAS than it was before you increase the KV, okay? And the change more than compensates in terms of dose. So always keep that in mind. Sometimes people are confused a little bit about why there's a difference there. Why is it that sometimes people say to me, increasing KV increases dose to the patient, and I read somewhere else, increasing KV results in decreased dose to the patient? And the key to that answer is whether there's automatic exposure control involved in that situation or not, okay? This automatic brightness or dose control that we talked about, automatic exposure control, it uses sensors and sophisticated software to determine and adjust primarily the MA. Then if it can't get a decent enough quality image because the patient is so large, it'll start to bump up the KV. But remember, we don't want to do that because we want the certain contrast. Bumping the KV is going to reduce our contrast a bit, so it'll do that secondarily. It may change our filtration or do some other things. And the manner in which those are adjusted is a little bit complicated beyond the fact that MA is the first choice. What is this? This is our filtration. This is the filtration, the additional filtration that's put in front of the beam. Remember, that's going to increase the average X-ray beam energy. It's going to increase the quality of the beam. It's going to decrease the beam intensity. But with automatic brightness control or exposure control on, that's going to get compensated for with an increase in the MA or MAS, okay? It doesn't change our spatial resolution. Here's our button for our grid, okay? Here's the grid. So if you push this button on the Siemens, it will either put the grid in or take the grid out. Currently with it white, the grid is actually in place. So if we're doing a pediatric patient, right, we really want to make sure that we've taken that grid out there. It results in decreased scatter, so it improves our contrast resolution in our image. It improves our image contrast, but unfortunately results in increased dose to the patient, so let's not use it in situations where there isn't much scatter in the first place, okay? It doesn't change our spatial resolution. This is our fluoro mode, whether we're doing continuous fluoro, pulse fluoro, cine fluoro, a DSA. That's the button right there that will control that. Make sure you've got it set the way you want, right? Going to pulse fluoro, the slower the pulse, the better the the lower the dose to the patient. It actually gives you better spatial resolution. But sometimes that strobe effect is a little bit bothersome and irritating. And if things are happening rapidly, the pulse at the lower rate may be too slow to see the anatomy that you want to see on, let's say, a swallowing study or something like that. So, you know, you've got to make the setting what you need it to be to see the pathology that you're looking for. It does result in a bit noisier imaging. I mentioned the strobe effect, right? We're going to use continuous fluoro, cine fluoro, and DSA only if needed. By the way, increasing levels of dose as we go up across those. This is the button that selects the type of contrast agent, and as you can imagine, when you hit that, it sets the KVP on the X-ray tube to match to that well, which is why we don't want to go adjusting the KVP on a contrast study unless we absolutely need to, right? We're going to bump our MA first to get our noise level about the area where we want. And then, so that's the contrast selection button. I just mentioned those two things. Of course, we can move this flat panel detector up and down. We want to get it as close as possible to the patient. Remember the R-squared effects. If we'll get it as close as possible to the patient, the spread of the radiation will have been less, and we can actually get by with a little bit less exposure. Not to mention the fact that getting it close to the patient means that more of the radiation is striking the II instead of potentially striking you as the operator. So it's better in terms of dose there as well. So get that as close as possible. Certainly you don't want to hit the patient with it, but decreases dose, as I mentioned, decreases scatter primarily to you. I always like to lock it in place if I'm doing the type of study which allows for that to be done. Here's where we can move the patient left or right, up or down. Move the patient so that the region of interest is centered in the field of view. That allows you to collimate maximally or magnify if necessary. I'm going to talk about magnification in a second. And this minimizes any parallax that might occur. So really in terms of the best image quality, get the region of interest that you want to look at centered in the II. Leave those lead curtains in place if at all possible. It significantly decreases the radiation dose to you. Unfortunately, because of backscatter, it does minimally increase the dose to the patient. These are our collimators. Collimate as aggressively as possible. If you only need to see a particular area, remember, collimation is the one thing that we can do that improves image quality while reducing dose to both you and the patient. So collimate as aggressively as possible. Because of that decrease in scatter, it really improves the contrast or the contrast resolution in our image. And here are these magnification modes. And I tell you, really use them sparingly, especially on old II systems. Because on old II systems, if you magnify down to a smaller region, your minification gain is reduced, right? You now have a smaller area being projected onto the II, so there's not as much minification gain. And so therefore, the amount of MA is boosted by the automatic exposure control to keep the brightness of the image about the same. That isn't quite as bad an effect in digital imaging systems where you can digitally boost the brightness of the image instead of having to do that. But you do pay the price of the image being a bit noisier there. So only magnification, I always say the residents, right? Magnification is not the same as collimation. Right? If you can see the structure well without magnifying, collimate in on it aggressively. Don't just magnify up on it, okay? And that'll help keep the dose as low as possible. I think I mentioned all these things. This is our button for fluoro spots. And back in the II days, you know, we had to use that because basically when you hit that button, you were taking a picture of the output on the image intensifier. But we have much less need to do that now where we've got a last image hold, where the image that was currently obtained while you were fluoroing on your pulse fluoro mode stays up on the monitor, and you can just ask the tech to save that rather than taking an actual fluoro spot. That image was acquired with 1/10 the dose of if taking a fluoro spot. So certainly use the fluoro spots if you need a better quality image, right? You need an image with less noise to really show a structure very well that you're not seeing well at the lower dose levels of fluoro. But do that very sparingly and use that last image hold feature whenever possible. I always say, right, fluoro is for looking, not cooking, right? If something's not changing, don't keep fluoroing, right? In today's systems where that last image hold stays up, if you're just not sure about something, but you need to look at an image for a little while to see what's going on, and it's not a dynamic thing, just get your foot off the pedal and look at that image and learn that. Getting your imaging time down will really be one of the best things that you can do in terms of keeping the dose as low as possible during fluoroscopy. And I think that's it.